Sander absent. All right, only these two. All right, we have one example left from I believe chapter 6. Of course, with some simplification as usual. And then we want to switch to project. Before I forget, next session will be reviewing for the task that was pre-scheduled for next Friday. So make sure you bring on your laptop again. So I have to develop something again for the first time for this particular class. I want to give you lots of examples. So that's that. And then I did submit your midterm grades on Blackboard. For every grade that you see, you should be able to click on it and then see the calculation details. If you've not done so, please do so. For homework, the same way. If you submitted your work, provided that you follow the policy, which was you got the 3 numerical ones correct, and then you submitted work for the 4th one for partial credit, then I'm able to grade that one. Then make sure you do open that because I give you feedback there. You don't say, oh, I got the grade and that's it. I always give feedback if you follow the policy. So that's about that. I posted the project spec sheet on Blackboard and then with 2 assignments with due dates defined in the spec sheet. So after this, we'll go over that, and I expect today will be maybe a little shorter session than the other sessions. All right, with that said, let's do our usual review of what we covered last time and make it from Aidan. Aidan, last time we went over, we said bending develops 2 types of stresses. One is normal stress, one is shear stress. So can you please give me the equation for bending, normal stress due to bending? So you're welcome to write it down. It could be part of the test. And you two please prepare for shear stress. We have 2 geometries. Sturdy, you give me tau max for rectangular, and then you give me this for general. Hey, we did so many examples last time. Sigma, normal stress due to bending.
My notes aren't very organized. I think I got it.
So you don't have your equation sheet with you?
Yeah. Is it MC over I?
It is. The left side, when you say equation, 2 sides.
Sigma
Yes.
sub M equals
Sigma.
sigma
Yeah.
equals
MC.
MC over I.
Very good. Sigma equals MC over R. All right, 30. So, shear stress equation due to bending for rectangular, or basically special geometry.
Is it from you to the array?
And the left side, the equation, 2 sides. It's tau, right? Tau max.
Tau max.
Yeah, tau max. All right, and Dylan, please give me the one for general.
Tau equals VQ over IT.
Very good. Remember, that's general. It does work for rectangular cross-section as well. But it's just more work. Dylan, point. All right, what else we did? Nick, where on the cross-section shear stress due to bending is 0?
Right in the middle.
Very good, right in the middle. You said like this. I mean, where is it?
Yeah, bend like this, right in the middle.
Right, in the middle. That's where shear stress for bending is maximum. Nick Reese point. And Jesus, where normal stress due to bending is maximum. Yeah, so suppose that imaginary shape, you bend it downward.
Bend it downward.
Bend it downward. Where is the maximum? Maximum elongation gives you maximum stress. Where is it?
Either end.
Either end, you mean outer or
Oh yeah, outer.
outer surface. When you bend it downward, which one is positive?
Positive will be on top, negative will be
Up.
on bottom.
You bend it like this, which one is positive?
This is positive,
Very
this is
good.
negative.
So on this one, it's maximum positive,
Maximum.
maximum in compression,
So front and back.
right?
Yeah, front positive, negative back.
All right, this is the point. Ray, that is what else we better learn. In tau equals BQ over IT, what was the definition of T? What did we mean by T? It's not the drink tea, right?
What equation was it?
Tau equals BQ over IT. What is T then?
Oh, is it the moment?
The lowercase t, the denominator. So Braden, then my feedback to you is this: you don't have good notes. That's the issue. When you put the equation down, or everybody else, please put the definition there. T is, I saw so many people. I don't know who was the first. I'll go for all of you guys. Go for it.
Thickness.
Agree? Agree? All right. Thickness. 4 people, Braden, told you that, so do not forget that. T is the thickness. Braden, you're not smiling today. Braden, you're not smiling today.
Oh, I just can't find it in my notes. Am I starting to believe that?
It is in here, right? T is the thickness. 20. Where's my pen? You see here, TA, it says this. T is the thickness. Where the- You see, even I wrote it here.
Oh.
Braden, here,
Okay.
okay?
Oh, it's the
All right, so let me give the points to
Found it.
It's fine. I understand that. It's like this.
Josiah, Jacob, PD, Olivia, and Justin. All right, Kiro, okay, let's do this again.
Oh, problem.
Yeah. So this is a practical problem. This is an inverse problem. Normally, we're given the load and the response is interested, but this is the opposite. So that's why we call it inverse. An inverse problem tends to be harder because we have to work our way backward, and because of that, it's not as easy. So I give you time. As you're writing this down, open question to everybody. What kind of material do you think it is? And why? Just
It is a ductile material because there's only one factor of safety.
one factor.
Or one ultimate stress.
One ultimate stress. All right, Jacob, what did you want to say?
I forgot, that's what I wanted.
Any other people? So, you see that it specifically says material's tensile strength is this. Does it say anything about compressive? So we don't know that. If it were equal, if it says material's strength, sigma u is this, sigma u is this, then we know that it is ductile. But here the wording is not as clear. I'll give you a point for that, it's not as clear. It says tensile is this, that the tension is this, sigma ut for sure is this. But sigma uc, can we infer anything? Could it be the same, could it be different? Right? So because of that, we cannot for sure say that. For sure we can say sigma ut is this. Nothing is said about sigma uc. So be mindful of these little nuances. We're engineers, we're expected to be precise. All right, so this is sigma u. Sigma u at t. And this is tau ut. And you said when the factor of safety of 2 is involved, you simply divide them by 2, and you get these as your new capped values. All right, before I start solving this with Kiro, another question. Guys, really this course, there's a lot of repetition. If you pay attention, if you get them once, you got it for the time. If you did not get that, that means you've not been listening for all of the sessions, to be honest with you. Now, open question. When it's asking either this or that, the procedure is the same. Whether it's ask you for maximum force or basically maximum load or minimum dimension, how do you solve it? Kiro.
You would take the maximum force and then divide it by the factor of safety to see, I guess, the most allowable amount of force to check.
Almost, not the force. What? The course is about? I know, in front of everybody I'm stressing you, but
Say it one more time.
I know that in front of everybody I'm stressing you, but what is the term?
Of the class? Solids, right? What? What?
Yeah, I know you're stressed. No clue.
What was the question?
You're stressed now, I see that. You're stressed.
He's asking.
Yeah, I don't watch. Yeah, I don't watch.
Yeah.
What was the question?
The
I thought it was.
You forgot this question.
Stress? Oh.
I keep saying that.
Oh, my, yeah.
Yeah, so it's all about stress, right? So you push the material to stress limit. Reagan, you remember that? In leg 1? You push the material to stress limit. Out of that, you get either the max force or min dimension, whatever is required. Right? So how many stress types we have here? You said it's bending. So 2, right? Normal stress and shear stress. Because 2 are given, if it does not say anything about compression, then we have for sure 2 of them. 1 for normal stress, 1 for shear stress. Had this been brittle, 2 for normal stress, 1 on the top, 1 on the bottom, and the shear would be in the middle. Right? So these are the 2 conditions. So 1, sigma, you said, do everything for stress. So sigma u over factor of safety, this is what we did in test 1. Equated with sigma max, and then tau u over fs, set it to tau u. Again, whatever stress type is applicable, you run that like this. And in particular, sigma u comma t in this case applies. And where is it happening? Sigma ut. In this case, you load it downward.
Yeah, so if it's a little downward tension is happening at the bottom.
Very good. So it's happening right in here. So you said sigma ut, so that's critical in sigma. And then in here, let me choose actually a different color, maybe green. All of this in the middle. Critical in tau. Because the material property compression is not known, we're not setting any restriction on the top face. All right, here are the point. All right, once you develop the equation, do substitutions. So Jacob, please remind us the two equations, one for sigma for bending, one for tau. But remember that it's rectangular, so use the easier one.
So for sigma, it is MC over I. Tau is 3B over 2A.
Very good. And C in particular is C of bottom, because we're looking at the bottom face. All right, point to you. All right, so Justin, if you recall, in bending, the first item was to put the coordinate system at the centroid of interest, right? Interest is point C. We have to put the coordinate system at point C, but at the centroid, the cross section is rectangular, that is right at the middle. So I have to put the coordinate system there. So right in the middle, these are the three axes that you go for X, Y, Z. Now, the bending, we think, is about which axis?
Is it around, it is around the Z.
Yes, very good, very good. Yes. So could you let everybody know what you did? And that was correct. What did you do to figure out that Z?
I just kind of visualized it and I just bent it down and said, all right, well, it's kind of looking like it's going around the Z.
That's it. The approach is exactly that. We exaggerated the deformation as you said, and see it curves around which axis. So write it down to figure out which axis. Ask this question. It curves around which axis? All right, you said about Z. We can pair our choice. This is Z in this case. All right, now we're able to, let me give the point to Justin before I forget. Nathan Smith, if you feel comfortable, please give me the C bottom value. And this is Z. So make sure you do have the definition for C. Do not disappoint me, guys. Write it down, make sure you don't have to calculate it. So C bottom. Yes, calculators are it's good. Anything you remember that? All right, Josiah, remember that? C bottom, what is it? So I kept asking you guys, please write it down. You're not listening. Even to your advantage, you're not listening. It's not the way to success. It's really not the way to success. That's the fact. All right, who knows that? I'm asking these two. Olivia, go for it, and then
Would it be 2 times 10 to the negative second?
Drew.
Yes.
What do you want to say?
Yes.
What's your answer?
It would, no, it would say the same answer, 2 centimeters, yes.
All right, very good. Each point, that's correct. So the instruction for that was we said, once you figured out the bending axis, you put at the centroid, right? You put these arrows, go in either direction to get to that point. Bottom is 2 centimeters away from that, and as Olivia said, it's 2 times 10 to negative 2. All right. IZ, Cole, please give me IZ. Rectangular, I, 4 rectangle, about Z.
1 second. Okay. 4 times 10 to the negative 2, and
It
then,
starts with something else. Say
Okay.
that first. The coefficient.
oh.
Jack is so ready for it.
Oh yeah, 1/12. So 1/12, and then the area, so, 4 times 10 to the negative 2 times 3 times 10 to the negative 2.
That's
Right.
it. 1/12 of area is J, is I.
Oh, and then there's the cube somewhere in there, so cube would go over the base, so, 4 times 10 to the negative 2, and then 3 times 10 to the negative 2 cube, right?
I saw Ethan first. Go for it, please.
Do you want me to just give the equation or the whole?
First, say the overall formula so that you remind him. I know that he was absent last time. He didn't get one more review chance like you guys.
So is it 1/12 base times height cube? Is that what you're asking for, or do you want me to?
Yeah, how else do they say that? You were not sure whether it's base or height that should be cubed.
Oh, how can you tell? It's whenever the force is on, depending on the axis of the force, right?
Certainly. Then Olivia, I think she was the second, yeah.
Is it perpendicular to the bending axis is the one that's cubed?
You see, it seems she has a great handwriting there, great notes there. You see, she's answering everything. So the issue is this: some of you do not have good notes there. If you were not really attentive at that time, it happens. Either get the notes from your classmates or come to me and take a picture of this. Please do that. So 1/12, as she said, base times height. One of them cubed, the one that is perpendicular to the bending axis. The other one should be cubed. And if you're not attentive in the task, 1 or 2 questions like this shows up, and then you easily lose points there. Or you easily get those points there. So it's perpendicular to Z, and it's 4, you cube that. All right, that is there. Cole, what is sigma UT value in this case? But I put the 2 here. I did not do the division. So before that, basically you were saying 450.
Okay, so 450 times 10 to the 6th
Very good. And tau U value,
was 80 times 10 to the 6th.
all right. And then area,
Would that just be 4 times 10 to the negative 2 times 3 times 10 to the
very basic, these 2 values, right? All right, point to you. Guys, again, it's really coming from a clean heart. I care about you guys. And you see how I'm working with each and every one. Write these down so that you do not miss these little things. All right, so the thing is this. M and B should be related to the force, which is P. M and B are applied at C, but P is applied at another point. So this means we really need to do static analysis. So I'll let you finish this, But you want to go to the next slide, do static analysis, figure out that dependence between Pn, M and B, and then all goes back into these two equations and then solve for these. But before that, yeah, write this down. Drew, you don't have to calculate it now because you have to do other things. If you solve for M and B, those will give you something about point C. It will not give you anything about P. So that's why you have to hold on to that. You're writing this down. This problem is very applied again. For instance, for mini balls, look at the two ends as the tires, and the load P could come from the weight of the driver or all the components of the car applied at that center, let's say, that centroid. And then we want to know for some reason whether the material at C is strong enough to handle the load, or how much load it can take, given the properties of point C. So some might really relate well to it because you're working on it in practice in a club. But that's how we would do that. So we want to do now static analysis, again, to relate P to the load at C. So let's do that in here. So static analysis. Disjointed at A and B. A is a roller from statics. It has two unknowns because it impedes movement in X and Y. And there is impedance, and there is resistance, and there is basically force. B is a roller. It allows movement along X, but it doesn't allow any penetration to the surface, so only By. Static analysis means we have three equations: sum of forces in X and Y, and sum of moments about point 0. That sum of forces, the first one tells us AX is 0 immediately. So let's just figure out the one of either, basically AY or BY. Drew, from statics, do you recall? Suppose P is known. And you want to solve for AY in one go, meaning one equation only. I don't know whether the instructor taught you this way or not. Not to solve for all unknowns, but a selective set of unknowns, how you would do that. Because it's a bit art there, but easy to figure out for this particular problem.
And then you would solve for AY by taking it as a moment around BY.
Thank you so much. Thank you so much. Sum forces in Y does not work because both are unknown. So you take moment about B, you're not interested in BY, take moment about line of action of BY. It could be B or anywhere along BY. So let's go for B. All right, true. So again, let's do review. You got your point, but let's do review. This basically means this in math or statics. Summation means basically scan through your free body diagram, take moment of every load about point B, combine them to 0. If it's counterclockwise, set it to positive, otherwise negative. So, for instance, the moment of AY about B, to figure out the sign, I would do it this way. Assume an imaginary pin at B, flick it with the force of interest, being AY this time, and visualize how it would rotate. Clockwise or counterclockwise?
It would rotate clockwise.
Positive or negative, fair this choice.
Then make it negative.
Thank you so much. So magnitude of the moment is product of two things, force times normal distance. What's the distance between AY and BY? Again, just
Oh, wait, no, sorry, I missed a bit of stacking.
10. All right, give me now, move on to the next one, P. Positive, negative.
No, it would be positive.
Yes, P times,
P times 4.
very good. Moment of BY about B. 0, no distance, it goes through the point, so 0. So for emphasis, I put that. All 0, BY times 0. That's why we went for point B, so that we get BY times 0 in that equation. So this gives us AY to be 0.4 P. That's one relationship. Now that we found that reaction at point 2 Drew, then we break up the system at point C to expose the unknowns. Actually, let me put with the same correspondence. Here, from here, here. That's P. This is point C. And AY, we found that to be this. So, put V downward, M upward, and then Fxc, we know that this is 0, no other force in that direction. Let's call this M at C, and then let's call this Fy at C. So two unknowns there. We want to relate them to P. This is a separate problem now. Now, what's C? This is a static problem. Suppose P is known parameter. How will you solve for Fyc?
We can just take the sum of the forces in Y.
That's it. Sum of forces in Y. So plus 0.4 P because it's upward, minus P because it's downward, minus Fyc because it's downward. Set to 0. This gives you Fyc that we needed. It gives you minus 0.6 P. That's the shear force, or the V that we needed at point C. Vertical force. The cutting force. What's the point? All right, Evan, I see that you're ready. We are now interested in MC. How would you go about it? Remember, we have still 3 equations in statics. Sum of forces in X, Y, and sum of moments. Sum of forces in X, would it help?
No.
It gave us Fx equals 0 already, so that's it. Sum of forces in Y, we already used it, so 1 is left. Sum of moment. Now, about which point?
Point C.
Point C. It makes sense. In fact, it could be any other point, but C happens to be easier. So let's do that. Some moment about C. So help me. Start from left to right, please. Moment of this about C. First, is it positive or negative? Pin at C. Flick it to that force. Visualize. Clockwise or counter.
Clockwise.
Very good. Negative 0.4 P. The distance. A to C.
8 meters.
8. Move on to P. Is it positive or negative?
Positive.
Positive. P times
2.
2. Moment of Fyc about C.
0.
0. For emphasis. And the moment of MC about C.
0.
You take $1 to the moon. How many dollars do you have? $1. You take one moment about C. How many moments? one moment, right? The same moment is moment, right? So it's a free vector, so leave it as MC. So keep that in mind. Moment is a free vector. That's why it said event, you can go for any other point. So this gives us MC in terms of P. MC is 1.2 P. Point. Olivia Reagan, I saw that you were discussing. Are you good? Or good? So really from static analysis, we wanted only these two relationships, FYC and MC. I'll give you time, we want to plug these back into our equations from solids. Yes.
Shouldn't FYC be 0.4?
0.4 minus 1 here, right? Let's just here. So it's 0.6 P. Because 0.4 and then 1 here.
Okay.
All right, Tyler, are you ready? You want to go back to the previous slide? You're done? All right, let's go back in here. Let's plug that into here. Actually, this is just now substitution. We'll get back to later. So now do this calculation. Again, guys, please let me have everybody trust. So let's put this MZ, we said it is, and we're going after magnitude. So disregard the negative sign is 1.2 P, and then this is, so again, absolute value, this is 0.6 P. Now solve these two for P value in Newton, in kilonewton. Confirm that you're getting first one, sigma is 1.5. This one is 53.33. I expect you do that without writing it down. You should be just looking at your equation, plugging the values in your calculator through the cross multiplication approach that we went over in class. But if you do the way that one of you or some of you did in task, did through 4 lines, it's not the way to do it. Yes, it is precise, it is good, but it's not efficient. You're an engineer, you want to be efficient. Get it correctly in the least amount of time. If you forgot how that approach works, come to me after class, I'll help you. We did that so many times, cross multiplication. I will be looking at just these numbers and then putting them directly in my calculator. Once you confirm it, make sure you confirm both so that I give you 2 points. You don't have to come here.
I had a question.
Sure.
So this is for the second.
You see that that's the approach on it. So, alright, what about this guy? All of these values, you see. I know this 2 times that should be 2 times 160, so that multiplied by that. And then solve by we got the same value here. Cross multiplication. Multiply that by no, the numerator. You see that this is the numerator. The numerator and the denominator of this one.
So I missed that.
Just see that. So this is P is this, yes, comes all of this, either with 2, 3, 6. So this is 3 and beyond that. All of this, cross multiplication, 1 is in here. And divide by 1 is not in the same value. You see that all these are this value now? You see these right there. That should be 3, right?
You have to divide it by 1,000, right? I get 2.5.
Did you make sure you divided 80 times 26 divided by 2?
Oh, I'm doing this one. That's right.
Yes. Whatever is your same value.
Bless you.
So you should have, on this side, it should be equal to 2.25 times 10 to the 8.
Okay, now we are these, right?
Because you have to divide it by the base, so it would be
2. 2,000. Cool.
So for your left side,
Mine was a base.
for your left side, you show on your screen,
This is
Which
this is on the denominator.
which is 2.25. And divide that, it's like the stress multiple is 460. Divide that,
Is that-
because banknotes, you have to multiply by 10 to the 6. And then,
Okay.
IZ should be equal to 1.6.
Yeah.
Times 10 to the negative 7. Is that what you got?
I understand. Algeria, okay, so, Algeria, and then Bolivia to Reagan,
Let me do. Give me some.
Would you have to go to the
Drew,
No, you should have the 3.
Wasi, Dylan. Artists. So you saw what we did here? So we have two
It's a
ratios.
divided by factor of
We
2.
want to solve for P.
Yeah.
Whatever
When I
is
get to
off diagonal, the crossing elements, to P, just put them in the numerator. Whatever remain on the same diagonal as P is in the denominator. Confirm that this is what I just said. Look at that and do this.
No. Just put that right.
That's on the left side of you. And then you'll have, you have your C is equal to 2 times 10 to the negative 2, because that's the halfway mark on the
Yeah, 2 times. 2 to the 10 on negative 2.
and then your I would just calculate this out and then do the rest.
you didn't, make sure you raise hand for the two and the points. Okay. Four,
Okay, 9.
gray.
Default prompts. Let's target that. Yeah, we got you. 2 times.
Just so I know.
And this is for what?
All right, so now we want to see, any questions, guys? Oh, we're not done. Hey,
Then divide that.
who was the last person responded? Tyler was about to ask you.
I get 2
So Tyler, we have two values for the force. Each one is the cap value based on the strength
Every 2.5.
for that particular stress type. But overall, we should have one cap value. Which one is the most or more critical value?
Yeah.
3.333.
So it's either this or that. So think this way. When you say critical, you start from zero load. Is it safe? No load. It is safe. You increase it, increase it, increase it. The first value that you see is which one?
Yeah, 2.5. This one. P.
That is the critical one. So which one is it? 1.5. That's the
Those two.
one that you have to pick. So P max, that's why I put exclamation. It's a paradox. We have to pick the minimum of the two P's. So again, inverse problem, you see that's more interesting.
Something's wrong.
All right, Tyler, I give you a point.
Should have
With a little help.
1.15.
All right, guys, any question on this example? Yes.
So when we got FC and it's negative, since we assume the arrow is downward, does that mean it should have been upward because it was negative?
Yeah, the load is the other way around, but because we're looking at absolute values, you see, that's why I put the absolute value in here, then we're putting the absolute value, yes. But sign, static, just tells us the force is in this direction or that direction. For us, sign matters when we're talking about tension or compression. And we already figured out it's positive here, reduced it here. But for shear, it doesn't care really whether it breaks this way or this way. That's what we did. We put the absolute value. Any other question? All right, so what we want to do, now we want to talk about the project, but I want to act as one of the members of your team.
That's right.
Make sure you guys, each team have the leader submit 3 different local bridges. It could be local to the university or to where you live, so that you're able to extract dimensions. We're going to talk about it. So let's talk a little about this. Do 2 examples closely related to project. Mark this down in your notes. If you get back to me, if you ask me a question later, or how I should calculate this, I'm not going to respond. Because you should show some responsibility. So I'm doing that for you now. Write it down, mark it down, and take advantage of it, guys. So, we need shear force and bending moment diagrams. So why do we need that? So, if you happen to have had the chance to take a look at the spec sheet for the project, the goal is to basically analyze a bridge, whether it's safe or not. And we just did in the previous example that the top, mid, and the bottom surfaces are the critical surfaces. The top would be in terms of compression, compressive strength. The mid would be in terms of shear, and the bottom would be in terms of tensile strength. Because concrete is mostly used for bridges, so I said just look at the bottom face and mid face, not top face, because we know that brittle materials like concrete are really good in compression. So if they're good in tension, they're for sure good in compression. That's why we're looking at the bottom face and mid face only, not top face. That would be redundant. So for that reason, we really need to know what happens at each cross section in terms of sigma and tau. Previous example, tau we said for rectangular is 3 halves b over a, so we need v there. For sigma, we need mc over I, we need m there. Therefore, we need shear force and bending moment diagrams basically, because we want to look at the entire length. So this is basically a review for you from statics. So for a bridge like this is point load applied to here. If you're interested in shear force, and we said this is V and this is M, these two quantities, you break at a point somewhere in here, X apart. On the left segment, you put V downward and M counterclockwise. That's the convention, that's not my choice. And we put opposite on the other side to balance it. All right, so what are you going to get out of this? We just did one example for V and M. I'm going to show you another example in particular for a bridge. But eventually, you do either at a point, you get values at that point. For instance, in the middle of the two segments, these are the values, or you get expressions depending on how you approach it. If you do expression, then you know for every value, every point, what the values are. So this is much better, because with bridge, we want really to know the response at every point. But how do we do that? So this one is the one that we already did in the previous example. But we want to do this one now, in terms of diagrams. We want to develop expressions. So how do we do that? I said, for the review, let's be pinpointing this, which we're going to see in the bridge. So the bridge that I chose, suppose it has 10 meters, it's 10 meters long, and the load intensity, W or omega, 40 Newton per meter. For your bridge, yeah, it could be different length, it could be different load intensity. After we do this theoretical example, these two examples, I'm going to show you how to do practical extraction of these parameters. So really, a practical project. You do teamwork, and you do a practical problem, and you do what we learned in class. So the reason that I put the load in terms of distribution, just because the bridge, I guess so many people walked on it, so many cars driven on it, maybe at the same time. So really distributed load makes much more sense. So you have almost half the time to complete it. So take advantage of all the time. Please do not put it toward the last minute. 11th week, if you email me, I'm not going to help you. You have half the time to complete it. Everybody's busy for that week. All right, so how do we do that? So first, reaction force. Only one of them, like the previous example. We know that at A is a pin, so A acts AY, and B is a roller, so BY. So reaction force, that means the entire geometry. Entire load. Guys, we do this and then we take the break. All right, so first we do equivalent, so 3 equality lines means equivalent, not more equal. We convert the distribution into a point load and leave every other point load there intact. We know that the distribution is rectangular, so we put the point load at the centroid of that distribution, right in the middle. That means this is 5 meters, this is 5 meters. And the load itself is the product of the intensity times the length. So 40 times 10, so 400 Newton. Applied at the center. Now this is a new problem. We know that the x is 0. We want to solve for AY. So let's say AY. What is AY? Just one of them. What is AY? We need only one. Yes, this is a straightforward problem. It's symmetric. We know that each one should get half of the 400 Newton. So each one should be 200. But what is the statics procedure that we've done? As Drew said, you're interested in AY, you're not interested in AY, take moment about B. So minus AY times 10 plus 400 times 5, again this is repeated, plus BY times 0 equals 0. So AY gets 200 as expected. So I'll give you time, but after this we want to do B and M at some cross section. So Vx, V in terms of x, M in terms of x. What is x and what are these? All right, so what do we do? Let's switch to new color. So here, so we want to B and M be in terms of x. So I define some cross section, x away from point A. I solve for AY, so I start from A, take this as x. And then that segment, I draw that in here, and I redo the solution that I did in part 1 for this segment. This is how it's done in statics. So AY, we found it to be 200. And we said when you break it on the left side, you put B downward. And counterclockwise. And there's no horizontal one because it's already 0, so let's not bother with that. And that segment of distribution should be put there. This 40 is still Newton per meter, but the length is x. Okay, this portion of it, I redo that in here. All right, like the previous problem, I have to convert that distribution to point load. So this 200 remains there, B and M are there, but this distribution is 40 times length is 40x. That's the load, I put it at the center. So that means this is x half, and this is x half. The internal length is x. The load is 40 times the length, which is x. Now this is a new problem. Solve for B and M. The same way. Sum of forces y gives us V. I believe Wasi said that. So cos 200 because it's upward, minus 40x because it's downward, minus V because it's downward. Set it to 0. You will get V 200 minus 40x in terms of x. All in Newton because we work throughout in SI units. Newton for force. So we just solve for V in terms of x, so that is V of x. And Evan said for M of y, we do the same thing, just take moment about the right hand point, this point, x. So if I take moment about x, point x, 200, if I pin it at x, 200 is negative moment about x, negative 200 times x is the length. We're done with that, move on to 40x. Downward, it develops counterclockwise moment about x, so it is positive. Again, this is repeated, I'm just having a different parameter here. This is repeated, like the previous problem. So 40x is the force, the distance is x half. All right, V does not create any moment, so V times 0. As Tyler confirmed, what was it called? I forgot. The moment is M. It's a free vector, set it to 0. So M this way, 200x minus 20x squared after simplification, Newton meter. So this is the second one that we needed. And that's it. Shear force, bending moment. Yes, please make sure you take picture and do not forget this. Tyler, if I ask you, Olivia, we have these expressions available. Let's just practice a little bit. If I ask you, do you see that x is measured from point A? Right? All right. If I say what is x at point A, what will you say?
0.
0. Believe in yourself, yes. In the middle?
X over 2.
In the middle of this entire beam, what is x value?
Oh, 5.
5 at point B?
10.
10. All right, as easy as that. Now, Reagan, if I tell you, if I ask you, give me V at point A, what would you do? The expression is given. Believe in yourself. V is in terms of x. You see that?
Is it just the equation?
Yes, but at point A. What is x at point A?
0.
0. So what would be V at point A? Yeah, just do that.
200.
That's it. If I say what is V at in the middle of the beam, what would you say? what would you do?
It's half of it.
Yeah, what would you do? Just half of it does not, what would you do to get that?
Divide by 2.
What would you divide? You have the expression. In the middle of the point, in the middle of the bridge, what's x value?
X would be 5.
X would be 5. You plot x to be 5 in V.
So you multiply 40 by 5 and
200 minus 40 times 5.
200.
Whatever that is.
0.
Yeah, I'm saying whatever that is. You see that? So basically it gives you the value. Now if I tell you what is V at point B, what would you do?
Divide by 2.
Just say the procedure. So I wanted to check whether you got it. Assume you didn't. So V is in terms of X, right? If I say what is V at that point, put the X value for that point in V. At V,
Be 10.
10. You put X to be 10 in V, whatever that is. You see that? So that's what we call it distribution or equation. It gives us the entire behavior at every point. We do all this derivation for that reason. It gives us that plot, something like this, for instance, but for this object, something like this. You see that? All right. Then if I tell you what is M at A, in the middle, B, does it change? The procedure is the same thing. You just plug in the correct value for X in M. We're good? All right, you get the point? So once you got this, the plot that I asked you for, you plot these values. Make sure you just plot the absolute value, because the cutting force, it doesn't matter whether it cuts downward or upward. As long as it cuts, that's it. Just plot the absolute value. So we have this. I suggest we take a break now. Please come back by 11. I see 24 here. 11:34, please. Otherwise, it doesn't work. So with this problem, it doesn't work, but that's why it says it.
So I want us to use that.
Yes, so that it always works.
Okay, okay, that makes more sense, thanks.
think for that last problem, I think it's pretty good.
Hmm. Yeah, I got 1.5 10 to the 13th.
You're doing something. It's gotta be in your calculator because
Sometimes it works.
how are you doing 10 to the 8 over there?
Because that's what, yeah. 45 times 10 to the 6 divided by the factor of 2. I get 2 plus 2, 5, 10 to the 8. And then we set this.
Yeah, but how is it being written right there? What button are you using?
I just put in scientific if you use the whole number. Because if I do.
I know what that. I'm saying, because you had to write this part out and it gave you this.
Mhm.
How are you getting 10 like that?
Oh, yeah, 7. 10. And then I just type in whatever number. 8.
Oh, I don't know if you can do that.
Once you use E,
Yeah.
then you can write the number 8 and it's taking the sense. It's been a long time since I had to watch the videos on it.
Yeah, I've been using this. I've been using this calculator since the beginning here. I didn't even know that.
I wanted to spend money on to get the electric ones because
It's the same thing.
I know. Do I really want to? It's like I have a bunch of these for free.
This color, but it's all the same.
And I see some features.
Actually, I like this one better.
I always have an extra one if you want one.
No, I mean, I got this one now, but when I was like in high school, we had these ones, everybody got one of these. And I like, when I went to this one, I didn't like it, but now I'm used to this one.
They had a box of shitty ones. I used to scrap all of it. I used to have to clean the batteries through the cane.
Yeah.
So I had to clean the black stuff.
It is nice that you can charge this one, but it also is nice to have batteries too, because if you need it now, you can just put it on.
Yeah,
You can also charge them.
Oh, yeah.
Yeah, but you need the batteries to be rechargeable. I don't know what happens if you charge unrechargeable batteries. I'm guessing nothing good though.
forgot what time I said, but I think it's about time. Let's finish this last one. So far, we did static analysis on the beam. We said eventually you want to be able to calculate stresses and factor safeties. So now this part is solids. So keep in mind that for this problem, V that we calculated was 200 minus 40x Newton, and M was 200x minus 20x squared Newton meter. So having these that are disposed of, then the rest is straightforward. So tau max, again on the center, tau max, we said 3/2 V over A. So we just found that. Area is the same cross section as previous example. And we are after really absolute value, so put absolute value around it. And if you convert it to mega for this, becomes this times x megapascal. Again, at different points, you're able to calculate tau now with this equation. Just put the corresponding x value. Again, we're measuring that from the left point, from A. So now you're able to plot it using any software. If you took MECH 111, you have MATLAB. We also have access to Maple or any other software is good. Just make sure you crop all figures to x in the range of 0 to L. Do not put outside graphs in your plot. It doesn't make sense. So make it really technical presentation. So that would be tau. Again, this is just repeated. We did this example in our last lecture problem today. We're just substituting values. So sigma max, we said is happening on the bottom. MC of the bottom is repeated over I. And as before, we said at x, let me choose a different color. So at x, at this, really, we're taking x, y, z axes. We know that it's above z, as Justin said, IZ. So MZ, we just found it, 200x minus 20x squared. Yes, again, we put absolute value, but it happens to be positive through the length. So you don't have to put absolute value there. And then C bottom, let me not put x again, just multiplication sign now. So parentheses, C bottom, we know that this is z half of 4, 2 times 10 to negative 2. That's the C value, I believe Olivia and Drew said it. And then IZ, 112 base times height, one of them cubed. The one that's perpendicular to Z should be cubed, which is 4. So if you calculate these values and you simplify to megapascal, 25x minus 2.5 x squared megapascal. So this means you have normal stress along the bottom face at every point. Just put the value for x, and you have the value for that point. I'll give you more time. We need to calculate factor of safeties. One for shear, one for normal stress. All right, we have sigma max available, and sigma u and tau u are available. So if you want to calculate factor of safety, basically for each, once for tau, once for sigma, you divide the ultimate by the max value. Tau u is given for this example. Actually, it's already mega, so do not convert it because mega is canceled out. Make sure you do include the absolute value so the factor of safety is positive. You know that the minimum acceptable is 1. When you graph it, if you see that any segment below 1, that's unacceptable. Guys, you bring in laptop, the point is to use it for class notes, not really doing other things. I care about you guys, but you should care about yourself too. All right, so sigma u, just plug in the values, 600, 25x minus 2.5x squared. You get megas canceled out. You graph this 2, and whatever is below 1, you say is failing at that point. Whatever above 1, you say, okay, that's good, but with that factor of safety, how good it is. Obviously, you want both of them to be above 1. One little point below 1, you say the entire thing is doomed to failure. The bridge that you want to choose could be already a failed bridge, and you're calculating why it failed. So that could also work. So I also asked, therefore, combined factor of safety. What is that? Look at the two factor of safeties. Overall, we're talking about one bridge. How good is it? How safe is it? So we needed one factor of safety. So at every point, you have two values. Which one would you pick? Yes?
The minimum value?
The minimum value. In your opinion? Yes? Any other opinion? So it depends, Olivia.
Okay.
So I'll give you a point, but think about it. If you're the contractor, you want to say my bridge is really good, right? You go for the bigger one, right? That's what people do. But if you're the customer, which we are in this case, that's what Olivia said. You want to really go for the weaker one. It's not good. Oh, you're saying 5? No, I see it's 3 here. I would go for a 3. So for that reason, Fs overall or combined is the min of Fs tau and Fs sigma. So if you basically point by point when you're plotting, you should go for the minimum one. So if you're using Maple, for instance, if you develop everything in terms of x, the min command there, min, of the two will give you basically the min of the two. and then you plot that function. But as a graph, basically you go one point. Basically one is like this, suppose. The other one is like this. What would you do? That we do with green. So in this little segment, the smaller of the two is this. In this segment, the smaller of the two is this. This segment is the blue one, and then it's red, and then it's blue. Right? Basically, point by point, you go to the smaller value. That's the combined one. Make sure you include that one as the 7th item that I required there. I'll leave it before I forget. So that's really the math that you need. Once you pick the bridge, if you have L and W that showed up in here, and then you have the material properties, tau u, sigma u, then you have everything. That's the math. I want to do something more. I want to start from scratch. You go to the bridge, depending on the scenario, what you would do. I want to help you with that. But before that, any questions, guys? Thank you, Olivia, for the confirmation. Some of you are still right. I'll give you a little bit more time. Because this is replacing your final exam. So even though we keep talking about stress, at least that's why we're relieving stress toward the end of the time. So start early and then finish early. If you need help, just let me know. Do not make assumptions. Guys, ask. Do not make assumptions. Yes?
So I'm just kind of curious. So you have like these equations.
Right.
I can graph it on my calculator and find the maximum. Would that be a way of finding the factor of safety, is dividing
Got it.
the max over TU, or the ultimate?
Ultimate divided by max. Ultimate is the
Yeah.
cap value for the material. Max is the max that is observing. It may not be what the material can handle. But the thing that you said, you calculated one value. But this in terms of x is for the entire length. Where is the maximum? For one of them, it could be in the middle. For the other one, could be really at the two ends. So you plot it so as to see the entire profile. You would give me the entire thing, not just for one value.
Okay, I didn't know.
When you graph it, then you pick, just point to that location. The max along the length is happening here. You're basically plotting the max of max at every location.
Oh, okay. Okay, that makes sense.
Good?
Yeah.
Okay. All right, if you're done this, then I did this already. Write this down or take pictures so that we can talk about it. So suppose you went to the bridge, it has multiple pillars. What would you do? Pick the one that makes more sense, the one that is more dominant. And L would be the length of that segment. Area would be the area of that cross section. So we want our job to be as easy as possible. Do not overcomplicate it, guys. So what we learned in class, just put it into practice. So if you go for as flat as possible with rectangular cross section, that's the easiest. Otherwise, then you complicate things. For instance, in tau, we don't want to use VQ over IT, it's hard. We go for rectangular cross section so that 3/2 V over A is just easy. So keep that in mind, pick the one that is in line with that. Pick 3, but I'll pick 1 for you so that the class overall is just working on distinct beams, bridges. Yes, sir.
So if our bridge had pillars, you're saying that we would be only calculating for a section?
A section, just one. You remember here, we think about things as a simply supported beam. You see, 1, 1. You see the two ends? Go for it. Yes.
Do they have to be like
named bridges per se?
Not really.
Because like I could take the one that's right out in front of university and that's copied probably 50 times all throughout Flint.
Understand that, as long as it's different location, if you happen to pick that, especially give me the address, then that way you have more chances.
If I just stand on the table and then call it a bridge?
If you use the table to cross a small gap, then you're technically bridging the gap from the table to the table.
Yeah, what I would do, I would give you a point on the bridge, on that item, not on Blackboard. No, let's just make it practical, something that really exists around, make it fun. Because by the way, when you look at that introduction, I give, so how would you present it? Actually, the department, we've been talking about changing MECH 111 based on input from the dean's office to a new course. And in that course, we want to include other things like technical presentation. So what I did, the little thing that I could do in these courses that I teach, I try to include that in here. So if you look at that document that I put there, the technical presentation includes certain aspects. I included them there. Pay attention to those. If you do that, you're really doing the technical presentation. Do not go for fancy things that are not common. When you go, let's say, to conferences, people expect to see the whole things there. If you do something else, the person says, oh, this person must not be really experienced. So you want really to impress them. So the way to do is the way that I put there. I put a lot of ingredients there, how you would do that. So when you want to pick a bridge, AJ, then you want to entice the audience by saying, why you picked that one? I picked this, let's say, this thing, it doesn't help that, in that, yeah, idea. So you would say, I picked this because it's close to school and other people pass there, it's really critical because of this, because of that. Talk about the history of it. Do not treat it as a homework problem or a project for a class. Make it a commercial.
Table was mostly a joke, but
No, I got it. Overall, I want to relate to it so that everybody's on the same
Makes
page.
sense.
Yeah.
Thank you.
Wait, well, I go here.
What about like trusses?
So you mean the overhanging pieces. If you go for that, you're just overcomplicating things.
Okay.
It's your call. Right? Yes.
Is 10 the number of people and cars, or what is it?
And I will talk about that. N is the number of either people or cars, yes, of being able to fit on the entire bridge. I'll talk about that. But once you're done with writing this, I'll talk about it. So all the time I'll do this derivation from scratch. This is really what engineers do. And you see a lot of variables there, a lot of stuff. That's life. Engineers are good at analyzing things and they pick the right parameters. For instance, in test one or other problems, I emphasize there are a lot of parameters, maybe too much, or too many. You should not use all of them. The ones that are relevant, you should use them only. All right, I see that you're done with your writing. So I would go to bridge. I see that it has certain number of pillars. Let's say I pick one segment. Perhaps the middle one is most dominant. I'll go with that. That's the length. The cross section of that, again, I assume rectangular. I measure those or extract those by Google Earth, or the posting that is there, or calling the contractor. Any of those approaches. So L and A out of this will be found. So that's done. Then, remember in here, we did davy. So what is that value then? Load intensity or load per length. How do we determine that? I would reason that the entire load intensity would be summation of two things. The bridge material itself and the number of people or cars on it. So if you pick something that is car driven, neglect the people on it, because it's not much compared to cars. You can simplify it. But if you happen to pick something that is AJ, if it's pedestrian walked, right? There are some around. Then only people are there. So then you would basically do only people for that. So that's why I put slash. It's not division. All right, let's do one at a time. Then so let's do people or cars, just much easier. It's basically number of people or cars you can physically fit or comfortably you can fit on the bridge itself. So it's a simple geometric problem. How many can you fit? So you pick your car, you know the length of the car, how can you fit? Round it up. Round it up. Divide by length of the bridge, it gives you that quantity, times the number. So that's what then is known. So make sure, whatever car you pick, then talk about it. There you can be fancy. All right, so we have that. Now, what about W of the bridge, the material of the bridge? Then I reason that, so I'm looking for really weight per length, right? Weight per length. Weight, I know this, mass times G, acceleration. Take it as 9.81 in SI unit. And M, I reason that it's density times volume. Density times volume. If you went with flat, a rectangular is A times L, and L cancels out rho AG. So then here you need what is rho, what is M, and basically people on cars, what the size is. You need to these plus these two quantity. So we said this N is based on geometrical problem, but rho and these two, we have to know these. So I want to talk about this. So let me connect to internet. So now the thing is this, you go to the bridge, no way, it doesn't make sense that it's made of just one material. It's made of more than one material, right? Let's make this assumption, suppose it's made of concrete and rebar. Makes sense, right? You're not able to open that up and see what happened. So let's make this assumption, say, based on your understanding, you suppose it's 5% rebar, 95% the other material. Whatever property that you found for the two, take that average based on the 5% and 95%. We're good? All right, so we have that. Still loading. I opened this up already. So the website, one website, good website is this, mathweb.com. The internet does not help now. All right, mathweb.com is a good website for that. Material repository. And then, if you're not sure whether it's really what steel type of rebar it is, what concrete combination it is, composition it is, pick, if you were not able to find good information, go with an assumption and mention it. Go with that. It's fine. Again, my point is not to give you a hard time. No, no way. Make it easy as long as you do a good assumption there. All right, so in the text box here, previously, when internet was working, I put in steel and gave you lots of options to pick from. If you know the material, pick. If not, then go for one or two average. And then, for instance, I picked for stainless steel, and then give you all this information. And then you see how practical this course was. We talked about models of elasticity, which is E value, is given in here. Make sure you go with SI unit. Shear strength, tau U value is given. If it's given as a range like this, just average that range. Go for the middle of that range. What else you see that there? Yeah, compressive yield strength, sigma UT, sigma UC is given. Tensile strength, sigma UT is given. These values, you see that these are really practical terms that we've been talking about. Density that we need in this part is given in here. You can go for the mid value. The unit should be kilogram, not gram in SI. Convert it to kilo. So you have everything really at your disposal. That would be how you figure out the material properties. Again, if the material of the bridge for some reason had nasty type, we were not able to find that property in here. Anywhere else you found, just cite that is fine. Yes?
Are we able to, if we're the ones selecting the teams, are we able to choose or have people from the other section?
No, treat it as a different class because otherwise I saw some issues. So yeah, treat this as separate class, please. All right, that's what I wanted to say. Any questions, guys, for me? Thank you, Nathan. Make sure you start early. You have questions, come to me, I'll help you. But do not please leave it to the last minute. If you get back to me on 11th week, I will not help you. Be responsible. You have almost half the term completed, and you have my help. Do not make any assumption unless you're sure, otherwise simply ask. I'll help you with that. All right, make sure you bring in your laptop for next class to prepare for the task.